All right, dipole-dipole interactions is this interaction between two poles. Okay. All right, let's start with right here. This type of interaction comes from the difference in electronegativity. Give you hydrochloric acid molecule as example. So chlorine is more electronegative than hydrogen. So the electron in the bond is go toward chlorine, and chlorine becomes slightly negative. So we use partial negative sign, right? And hydrogen become partial positive. So look something like this. This is chlorine, this is hydrogen, and that. So the electron density, so the red one right here, goes to chlorine, and hydrogen have electron deficient area. All right, so partial negative here will attract the partial positive of the next atom. All right, so there's attraction right here, so we call dipole-dipole interaction, the interaction between two poles. Okay, all right, HCN, can you tell who's partial negative, who's partial positive? The nitrogen, that's a partial negative, right? And the hydrogen on the other end is partial positive. Okay, so the partial negative will attract partial positive of the next atom, and a partial positive will attract the partial negative of the next atom, and goes all the way like that. All right. Since the charge is not a real charge, it's just a partial charge. So compared to the charge from the ionic compound, the quantity of Q here, the charge is not as high. Okay, and that makes the dipole-dipole interaction is all right. Right, so not that strong, but it's all right. It got something. All right, so we have if you look at right here, so the larger net dipole moment, so acetonitrile have a big net dipole, so go toward nitrogen, right? And stronger the interaction. So what is it? That large dipole, the boiling point go up to 82 degrees. Sulfur dioxide, so the difference in electronegativity between oxygen and sulfur is not as large as the difference between nitrogen and carbon. Okay, so the dipole is less, so the boiling point is lower. All right, and carbon dioxide, this guy is totally non-polar, so there's no dipole moment, so zero there. The boiling point is really low. It's not even a liquid at room temperature. This is a gas. Okay. Sulfur dioxide also a gas, but has a higher, like much higher actually boiling point than the carbon dioxide. Okay. All right, so we got a concept test real quick. So formaldehyde, so Ch2O, so all these are formaldehyde, can form dipole-dipole interactions with other formaldehyde molecules. So they can form dipole-dipole with another molecule, Determine the structure of this compound and assign partial positive, partial negative to an appropriate atom, and then draw lines to represent the dipole-dipole interaction. Okay. All right. Start with this molecule. So we can do it together here. Between carbon and oxygen, I'm not going to talk about CH bond. CH bond is non-polar. All right. The polar bond is C double bond O right here. All right. So who's partial negative? Oxygen. Good. Oxygen is more electronegative atom, so the electron will spend more time on oxygen. Right. So negative, delta negative on oxygen and delta positive on carbon. Same thing happened to the molecule next door, right? And also the same thing the molecule next to it. And all you have to do, the dipole-dipole come from partial negative to partial positive. So negative here to positive there. That's the dipole-dipole. Negative here to positive there. Dipole-dipole. Don't draw negative to negative or positive to positive. They repel. Okay. All right. And negative to positive, you can do that too. Okay, all right, that's dipole-dipole interaction. Now we're going into hydrogen bonding. If you don't get about the dipole-dipole interaction, I recommend you go back and watch one more time, because hydrogen bond gonna use what you just learned about dipole-dipole and explain in here. Okay.